In this third step in our example D6 with the asymmetric frame, we're going to write the equilibrium equations, and we get the typical scenario of we've got the free degree of freedom of the rotation at B, giving us then that the sum of the moments that frame into that joint, and only that joint, MBA plus MBC, will be equal to 0. Substitute in with our shorthand that B stood for EK theta B, etc. Right, and that gives us our equation 1. Same thing at joint C, and that takes care of our two joint rotational degrees of freedom. But we also had sway in the system that was ultimately tied to 1 degree of freedom, that is the delta, the amount of sway that's going on. Right, and so there we start by writing a global free body diagram, and we've got our 80 kip applied load on here. We've got the member end moments shown in the positive sign convention direction. We've got to get those correct and consistent. That's what correct means, is to be consistent with our sign convention. Now the end axial forces and the end shears, or the reactions there, these can be arbitrary just long as we're now consistent with the rest after that. But there's no particular sign convention that we have to have for those. There's a reason why you might want to actually take these in the other direction, and that is associated with the column free body diagram, and that in order for this to actually be working the way it's shown, that if both end moments are clockwise, then both end shears will have to be opposite as shown. But it doesn't really matter as long as we're consistent with this free body diagram over here to the left. Haven't shown the axial forces because they don't turn out to show up. Some moments about the top, and we get the sum of these two moments has to be opposite of the couple that comes from the end shears, or AX times 6, and so there's your opposite sign there. Likewise for the right column, of course the moment arm is half of what we had before. Okay. And then we go back to the global free body diagram, the way things are shown, and we have been consistent. Then AX is equal to the opposite of DX. So that allows us then to substitute in terms of member end moments. That AX is equal to the sum of these two divided by -6, and then the other one we can just only have to divide by 3 to get to the substitution that we really want. And then that can be simplified down into 0 on the left hand side. Take this on over, clear out the 6's first, and you get just the sum of all these moments. There's a change in the coefficient because of the 6/3 business, and then we can substitute in for the various terms, right? So MAB is, go back to our slope deflection equation, was 10B minus 10D. That's the first part. And then MBA has 20B and a minus 10D. I wrote it sort of staggered and different because I knew that these terms would get added in a likewise fashion. And then over here with the MCD and MDC, we're doing the same thing. You have to remember to multiply the 2 all the way through. I did that successfully in the first term, messed up the second term. So that's supposed to be another 40 that's sitting there. The way to make things more clear is always to write on top of the mess that's already there, right? So 40D. And then you add that up into a nice simple equation. 0 equals 30B plus 120C minus 100D. And remember that B really means EK theta B, C really means EK theta C, and D really means EK delta. Recalling that we've already absorbed that psi is equal to delta over 3. That's the chord rotation term for one of these. Another one, psi was equal to delta over 6, already been included, and so that we end up with just that as our symbol that we're using in that equation. Alright, so there's your 3 equations of equilibrium, and now we can go about solving those to find the individual member end displacements and the amount of total sway.